dans cette présentation, il y a la partie contexte et introduction, elle est un peu longue, juste pour introduire le problème. Je pense que c'est plus intéressant d'introduire le problème.
Pardon, Riyadh. Riyadh, pardon. Juste une question. Je peux enregistrer?
Oui, oui, oui. Oui.
Ah, désolé. Donc, j'enregistre. Hein.
OK, très bien. Donc, la présentation elle-même, la plus grande partie, c'est l'introduction et le contexte. Et la partie solution, c'est un peu court, mais beaucoup plus, je vous invite à lire le papier. Donc, c'est un article qu'on a publié le mois de mai précédent et dans la conférence SysML, Systems for Machine Learning, et qui a eu le meilleur prix le prix du meilleur article dans cette conférence. Je vous invite à voir si vous voulez plus de détails. So the presentation is about a deep learning-based cost model for automatic code optimization. So as you see in the title, the goal is to do automatic code optimization. That means building compilers that take code as input and automatically optimize it to generate very fast code. And then we use deep learning cost model inside those compilers to enable compilers to make decisions. So I will explain all of this. I will explain the problem and then why do we need cost model in the presentation. So one of the long-term goals in our community, in the compilers community, is to build compilers that take high-level code, something, let's say, written in language like MATLAB, and then to automatically optimize it and generate very efficient code for the hardware target, for a given hardware target. And then during this presentation, I will show you an example of a system that solves this problem. So if you look at compute-intensive applications, they are everywhere. You see them in deep learning, you see them in image processing, you see them in bioinformatics, in scientific computing. And accelerating computations in any one of these areas has a huge impact. If you look at deep learning as an example, this graph shows the increasing need for computing power in training different neural networks. So you have here these points are different neural networks. And the graph shows the amount of computing power. This is on the y-axis, the amount of computing power needed to train these neural networks. And here on the y-axis, you see the years. So you have AlexNet that was created in 2011, 2012. And then you have things like AlphaGo Zero that was created more recently. The difference in amount of computing power between training AlphaGo Zero and training something like AlexNet is orders of magnitude. You need 300,000 more computing power to train AlphaGo Zero compared to training AlexNet. And while single GPU is enough to train AlexNet, you need cluster of GPUs or TPUs. These are the tensor processing units to train something like AlphaGo Zero. So there's a huge jump in the need of computing power. Let me take a more concrete example. If you look at XLNet, which is an example of state-of-the-art neural networks in NLP, in natural language processing, training XLNet requires more than 500 TPUs, and you would need more than 5 days of training. So this is a lot of compute, and also very long time of training. And in order to train XLNet, if you would do the training on the cloud, you would spend more than $60,000. So that's very expensive. And that's just to do one training. And as you know, to train these neural networks, you need to train your model multiple times to try different configurations of your model. And so at least the real cost would be maybe 100 times this amount. And then if you look at the carbon footprint of training these neural networks, training something like the transformer architecture, which is state-of-the-art NLP model, would produce 5 times more carbon than what a car would produce in all of its lifetime. So again, that's a huge carbon footprint for training these neural networks. So as you see, training neural networks requires large computing resources. It's very time-consuming. It has high cost, and also it has high carbon footprint. And one way to solve all of these problems is to accelerate the training these models. And in general, accelerating the models, whether it's accelerating their training or even accelerating the inference, to enable the use of these models, let's say on your smartphone or on your driver's car and so on. And one way to accelerate the models is to do what we call code optimizations. And when I say code optimizations, I mean applying code transformations to accelerate the model execution. So I don't mean the term optimization that we use in classical machine learning, but rather modifying the code to make it run faster. Of course, you can also work on improving the model itself, designing models that are more efficient, and also on designing new hardware accelerators. So during the talk, during this presentation, we will not talk about these two parts, but rather we will focus on code optimizations. So let me explain with concrete example, what do we mean by code optimizations? Let's take the example of operator fusion, which is one of the code optimizations that you would need to do. So if you look at the following code, which is TensorFlow function, this function takes three vectors as input, the vectors x, y, z. It multiplies y and z with element y's product. It adds the result to x, and then it performs a reduction operation. If you run this code on TensorFlow, TensorFlow would create the following computation graph, where in the blue parts are the actual computations or kernels, what we call kernels. So here you are multiplying, or TensorFlow multiplies y with z, and then stores the result in a temporary array in global memory. And then it applies x plus t and stores the result again in memory, and so on. One way to optimize this code is to take all of these blue kernels and fuse them into one big operation. And the main difference is that now this operation, rather than storing the intermediate results in global memory, which is very expensive, it stores the intermediate results in registers, which is way, way faster. It's at least 2 to 3 orders of magnitude faster. So that's quite a big optimization. And now you just have single kernel, and you store the final result in the main memory. If you apply this optimization on a model like ResNet, you will get around 46% speed up acceleration. If you apply it on XLNet, you will get 87% acceleration. So that's an interesting acceleration with just applying this single optimization. But the problem is that currently this optimization is done by hand. That means developers have to write this blue kernel here by hand, which is which is not trivial thing to do. And the reason for that is that there is no library that implements this particular fused kernel, simply because there is an infinite number of possible expressions that can be fused together. And because of that, it's just impossible to write all of them in single library. So no matter what you do, there will be always expressions that are not implemented in given library, just because there is an infinite number of possible expressions. Our goal is to allow users to write any expression they want to write in machine learning models. And while some of them, like these, for example, are implemented in libraries and are highly optimized in libraries, many other expressions are not implemented in libraries. This is why Elon Musk tweeted some time ago. He said, he was talking about what they do at Tesla when they develop neural network models. He said, our neural network models are initially written in Python for rapid iteration, and then they are converted to C++, C, and raw metal driver code for speed. He says this is important. So engineers at Tesla, initially, when they are designing their neural network model, they write it in Python just so that they go fast. And once they figure out the model, they rewrite it in C++ because, and then when they rewrite it in C++, they optimize it. And the reason for that is to make it run faster so that they can run it on the Tesla car. But doing this operation is requires a lot of expertise, is very time consuming, and is error prone. So in general, it's very limited in terms of application, and only very big tech companies can do that. So our goal in this project is to kind of work on solving this problem by automating the code optimizations and basically use compilers to automatically optimize such code for neural network frameworks. So as a user, you would write, let's say, your neural network model in PyTorch or in TensorFlow, and then automatically PyTorch and TensorFlow will automatically optimize your code and generate a very fast code. But automatic optimization, automatic code optimization is a very hard problem. And let me show you an example why. If you look at this simple line of code, this is the matrix multiplication algorithm. Here we are multiplying the matrix A with B and storing the result in C. The actual algorithm is very simple. You can write it in one line of code. But in order to optimize it, the compiler has to generate this very complex code that you see here. And in order to do that, it has to apply many complex code optimizations. It needs to make sure that these optimizations are applied correctly and that they compose correctly. And the biggest challenge here is in selecting the right combination of optimizations. So the compiler has a lot of optimizations, and it needs to figure out which ones of these optimizations should be applied. Because if you apply the wrong optimization, it will make your code slower rather than making it faster. And this is a challenging problem because first, you have millions and millions of combinations, possible combinations of optimizations. The search space is very large. Second, predicting the performance of optimizations is hard. For example, if you go to an expert and show them a given combination of optimizations and ask them, if we apply these optimizations on this code, are we going to get speed up? Is the code going to run faster or no? They might give you the wrong answer. So it's not even easy to predict for a human expert. And then also there are complex interactions between these optimizations. Sometimes if you take single optimization and apply it on the code, you don't get speed up. If you take another optimization and apply it on the code, you don't get speed up. But if you put them together, you get speed up. So it's not, the interaction between optimizations is also not trivial. And before going further, let me explain clearly what do I mean by the problem of code optimization in general. So the problem of code optimization, at the heart of this problem, or the main part of it, is what we call optimization selection. So the goal is to develop a module in the compiler that takes code as input, and then also takes list of code optimizations. For example, in this work, we are interested in high-level code optimizations. These are mainly ways to kind of transform loops so that they run faster. Things like what we call loop fusion, loop interchange, loop tiling, loop parallelization. Loop parallelization, for example, takes your loop and then makes iterations of your loop run faster. Loop vectorization, for example, makes your loop run using vector instructions. So these are just different optimizations. We don't need to get into the details of what they do, but basically each one of them makes the code or may make the code run faster. So the compiler has a long list of these optimizations, and it needs to select the best combination of these. Let's say it should apply, for example, loop fusion and loop tiling, or loop fusion and loop parallelization, for example. In this case, in the example, it chose to apply loop parallelization with loop tiling because this combination would minimize the execution time, would give you the best execution time. And the problem of optimization selection, we can model it as a search problem, where you can create search tree and kind of search that tree for the best solution. So let me show an example of how we can do that. Let's assume we have a very simple code that has a single loop, and within that loop we have single statements. So it's a very simple example. Let's call that, so single loop and single statement inside that loop. Let's call that loop C. Let's assume that our compiler has only two optimizations, tiling and unrolling, and that each one of these optimizations has parameters. So in order for the compiler to decide, the compiler needs to decide whether it should apply tiling or not, and whether it should apply unrolling or not, and whether it should combine them. And again, we don't need to get into the details of what's tiling, what's unrolling. You can just see them as black boxes, and each one of these is a way to transform the code to make it possibly faster. So in order for the compiler to decide whether it should use tiling or not, it should ask itself, should I apply tiling? And it has two choices, yes, no. And basically, internally, it has to use some cost model to compare the two choices that it has. So let's say it uses that cost model, and using the cost model, it decides that tiling is the best thing to apply. In this case, it applied tiling with some default parameters, in this case, 32, 32. And then the compiler would ask itself, what are the optimal parameters for tiling? And it has a lot of possible parameters that you can apply. And again, the compiler has to compare between all of these alternative choices and using cost model. And let's assume it picks this particular choice. Then it has to do the same thing for the enrolling optimization. So as you see, figuring out which optimizations should be applied can be modeled as, you can kind of express all the choices as tree. And then you can explore this tree using classical exploration techniques. Let's say things like beam search, A star, I don't know, Monte Carlo tree search, any favorite technique to explore this tree. And then also you need some cost model to compare between the different choices that you have. So the goal of all of this work is to develop that cost model. Basically, the cost model that takes the code and a bunch of optimizations and would tell you what's the speed up that you would get if you apply those optimizations. So as I said, the goal of this paper, of this work, is to build a deep learning model that we will use as cost model. And then we will use this deep learning model or this cost model for speed up prediction in this when we do that type of search. The model will take code and list of code optimizations as input. And then it will predict what's the speed up that you would get if you apply these optimizations. And speed up is just how much your code is going to be accelerated. It's basically the execution time of the original code divided by the execution time of the optimized code. So speed up higher than 1 means your code is running faster. Speed up lower than 1 will mean your code will run slower. Okay, so for the cost model, classically, in this, let me just go back here. Classically, people have been developing these cost models, but they have been developing these cost models manually, basically building them by hand, what we call analytical models. The problem of those models, they are not very precise. So the whole point of this work is to replace those analytical models with a deep learning-based cost model that's built using data. Before going into the details of the model, let me first, in 2 or 3 slides, talk about the compiler that we use, which is the Tiramisu compiler. This is the compiler on top of which we implement all of our automatic optimization work. And then I will talk briefly about the deep learning-based cost model. And finally, I will show an evaluation. So let's start with a brief introduction of the Tiramisu compiler that we are using in this project. So Tiramisu is a compiler for expressing algorithms and code optimizations using C++ API. So you have C++ API that would allow you that you can write to express algorithms, and then the form will look like something like MATLAB, and then to also express the code optimizations, basically specify how you want to optimize your code. I will show an example in a minute. And it's mainly designed for optimizing loop nests that manipulate arrays. So this is the type of programs that we can optimize using Tiramisu. And it's designed with 2 main ideas. The first idea is that it's designed to separate algorithms from code optimizations. I will explain that in the next slide. But the main idea here is that as a developer, you write first your algorithm, the pure algorithm, the unoptimized algorithm, and then you specify how that algorithm should be specified. And all of this, you do it using C++ API. And then the second idea is to use a mathematical model that we call polyhedral model. And this is a model that captures the semantics of the code, and we use it to model the code, model all the code transformations, reason about the correctness of code transformations, and so on. I will not talk about the polyhedral model. I have an extended version of this presentation, so if you are interested, I can send you that one, and it has all of the slides with all the technical details. So I will skip many technical details, and then so let me explain what separating algorithms from code optimizations mean in the next slide. So the main idea here is, as a developer, first you write your code, you write your algorithm, which declares the pure computation or the unoptimized computation. For example, if you want to express the following pseudocode, which is simple two-dimensional loop for x, for y, and then you are writing 0 in the array out xy, you can express this in Tiramisu as follows. First, you declare the two loop iterators, x and y, and provide the ranges, x between 0 and n, and y the same thing. And then you declare the actual pure computation. And here you are saying that we are storing the 0 in out xy. So you didn't specify, at this stage, you still didn't specify how this code will be optimized, or in which order these zeros will be written, and things like that. And then in the second part of your code, you have kind of C++ API, or what we call comments for code optimization, that you can use to specify how this code should be optimized. For example, if you want to parallelize and vectorize the code, this is what you should write. So you'd say out to parallelize x, this means that you want to parallelize the x loop. And then if you say out.vectorize y, that means you want to vectorize, to run the y loop using vector instructions. And this is an example of matrix multiplication written in Tiramisu, optimized in Tiramisu. The first part is the algorithm, where we just specify the computation. Here we declare the inputs, the arrays A and B, and then the output is C. So we see Cij is Aik times Bkj. This is the classical matrix multiplication algorithm. Basically, you multiply one line by one column, one line from A, or one row from A with one column from B. And at this stage, we still didn't specify how this code will be optimized. And then in the second part, we specify how the code should be optimized. So here the user is saying that the I loop of C should be parallelized, and then the ijk loops should be tiled. This is another optimization, and then vectorization should be applied, enrolling should be applied. I will not go into the details of all of these optimizations, but the compiler will take this input and automatically generate this output, which is the optimized code. So it automatically took this very simple description and generated this very complex, highly optimized code for you that would run on your CPU. And if I remember well, I think running this code is about around 400 times faster than, like running this optimized code is about 400 times faster than running the naive and optimized code. So it's quite a big difference. Okay, now that we have seen kind of an overview of what is Tiramisu, let's look at the cost model that we built on top of Tiramisu. And as I said, the goal was to develop a model that takes code and list of optimizations as input, and then predict the speed up as output. So let's start with a description of the input. How do we represent the input, which is the code and the code optimizations? Let's assume we have the following piece of code. It's simple code that has these for I, for j, for k loops. And then you have these computations, which are simply statements. So computation A is simply statement A. We use the term computation in Tiramisu which just means statement. So you have these bunch of statements. In order to model this input, to represent this input, we follow the same structure as the abstract syntax tree. The abstract syntax tree is kind of tree representation that we use in compilers to represent the code. So we follow the same structure as the AST, abstract syntax tree. And for each one of these computations, or for these statements, we use a vector to capture the features of this statement. We'll talk in a minute about what does each one of these vectors contain. But basically, if you look at, for example, the computation E, which is the statement E, it's inside the loop M, and the loop M is inside the loop J, and the loop J is inside I. So if you look at E, this is E, the statement E, it has a vector, and E is inside the loop M is inside J, and then J is inside I. So with this kind of tree structure, you capture all the structure of the code. Then let's look at the content of the E vector. So the E vector is a bunch of features that represent the statement E. And the first part that we have here is the operations count, which is simply a bunch of fields where we specify how many additions do we have in the statement, how many multiplications, how many subtractions, and so on. So it's simply a histogram of all the operations that we have in the statement. And then in the statement, we are accessing arrays. You have access to something like A of ij, or B of I, or things like that. We represent those using what we call memory access arrays. So we have these green blocks that represent the actual memory accesses in this statement. And then for the loops M, J, I, we also represent them inside the vector. For each one of the loops, we represent the loop extents, which are simply the where does the loop iterator starts and where does it end. For example, if you have M going from 0 to 100, you will write 0, 100 here. And then here we represent, we have a bunch of Booleans that represent the optimizations that we apply on that, on the loop M. For example, did we apply tiling? Did we apply unrolling? Did we apply parallelization? And so on. So these are simply a bunch of Booleans. And we do the same thing for all the loops. So the main idea of this representation is to do very, very little amount of feature engineering. We didn't do a lot of feature engineering. This is super simple representation where we just capture the basic information of the code. And the assumption here, or the hypothesis in this work, is that we want to build a model that takes this very simple feature, these very, very simple features, and then automatically predict the speed up. So it has to automatically build more complex features based on these very simple features. And now let's look at the model. The model is hierarchical LSTM that also follows the same AST, abstract syntax tree structure. And it has three main parts. In the first part, we take the vector that represents the computation, which we call the computation vector. And we use feed-forward neural network to create an embedding, which is another vector, here represented as the green vector. But it's basically another vector that would represent the statement. Then once we create all of these green embeddings, we go to the next step, which takes these embeddings, the green embeddings, and then combine them. So if you take this example, the yellow part here is an LSTM. So this LSTM will take sequence of statements, of embeddings of statements, or computation embedding vector, and then combine them together, and then create a new embedding that represents the whole loop nest with all of the statements inside that loop nest. And then we keep doing this hierarchically. So this M loop here is represented, or we use an LSTM that combines this vector with this vector, and so on. We just keep doing this hierarchically until we create an embedding that represents the whole code. And then in the last step, we have feed-forward neural network that takes this blue embedding and then predicts the speed up. Now the next question. So I have explained how do we represent the input? Basically, what are the features? What does the model look like? And by the way, we tried a lot of models to kind of figure out this model. We really tried many versions. We tried just feed-forward neural networks. We tried simple LSTMs. We tried 3 LSTMs. We tried a lot of models, and this particular model gave us the best accuracy. Now the next question is, what's the data that we are going to use to train our model. And the data here, the model is going to take, as we said, it's a model that takes the code, list of code optimizations, and predict as output speed up, right? So we need data that has these 3 points. The problem is that we don't have enough Tiramisu programs written to kind of generate this data. And we will generate it by running usually we will generate this data by running the programs. We just take an optimized program and run it, and then we get the execution time. And by checking that execution time, we can know what's the speed up. But we don't have enough programs written in Tiramisu. So the idea here was to generate random programs to solve this problem. We generated random programs. And for each random program, we generated a bunch of random optimizations. And we just optimize those random programs with these random optimizations and run them and get the speed up that and get the speed up. And by doing that, we got we built our data set. Each point in the data set is triplet of algorithm, list of code optimizations, and speed up. Our code generator guarantees correctness by construction, so it is designed to just generate correct random algorithms and correct optimizations, random optimizations. We generated 1.8 million data points, and the data generation took about 3 weeks on a cluster that has 16 nodes with 48 cores per node. So let's look at the evaluation. This is the accuracy of speed up prediction. So here we have the blue dots. We have a bunch of programs generated randomly, with also a bunch of, for each program, we generate optimizations randomly. We run them, and we use the model to predict the speed up. And then also we run them, and we look at the real speed up. So the measured or real speed up is the red dot for each program. So these are the programs, the list of programs. And I think in this case, we have about 400,000 programs generated automatically. And then here on the y-axis, we have the speed up. And if you take, let's say, one random program here, the red dot is the measured speed up, and the blue dot is the actual or the predicted speed up. So ideally, we want the predicted speed up to be as close as possible to the measured speed up. As you see, in many cases, they are quite close. So here around the speed up of 1, they are actually very close, almost the same. And as we go a little bit further from the center, we start to be a little bit less accurate. So here, for example, the predicted speed up is a little bit away from the measured speed up. But in general, you see that there is correlation between what our model predicts and the measured speed up, as you see. And in general, the mean absolute percentage error of our model is only 16%. That means in 84% of cases, it has an accuracy of 84%, kind of. The next question, maybe let me show you this slide, since I think we still have some time. So this slide goes a little bit in more detail into the error distribution across different speedups. So here on the y-axis, we have the absolute percentage error. These are the errors. The higher the error, the worse things are. And here we have the measured speedups. And as you see, around speedup of 1, we have quite high accuracy. But as we go a little bit further, the accuracy drops. And below the speedup of 0.05, the accuracy just goes up to 40%, or the error, sorry. The absolute percentage error goes to around 40%. And the reason for this is that the majority of the data points that we generated randomly had speed up around 1. And this is why our model is more accurate around 1, just because we have the majority of our data set is around 1. And then for speedups that are a little bit further from 1, we don't have a lot of data, so the accuracy drops a little bit. So that shows the kind of importance of having even more data than what we have. Now, you might say this model was designed by generating random programs with random optimizations. Is it going to be actually useful in realistic situations? when optimizing real programs. So let's see an evaluation of the model and using the model to automatically optimize code on realistic programs. And here we have set of, it's benchmarked with set of applications. Here we have, these applications are from the area of image processing, like box blur, which blurs an image, and then also from deep neural networks like convolution and ReLU, and things, and from scientific computing like heat2D, which shows the heat diffusion in 2D space and heat diffusion in 3D space, and so on. So these are a bunch of applications that we have evaluate on these applications. And then on the y-axis, we have the speed up over the baseline. The higher the speed up, the better it is. And the baseline, to simplify, let's say it's the unoptimized code. So it's by how much our model is accelerating, or how much is the output code being accelerated compared to the unoptimized code. In the first experiment, we use beam search to explore the space. And then we use execution to actually evaluate rather than using cost model, we use execution, which would give us the perfect evaluation of our of optimizations. And these are, so these bars, the blue bars, show the perfect optimizations that you would get if you have a perfect model, which is execution in this case. So this is the ideal case. And we will use this as a reference that we will compare to. In the second experiment, we still use beam search, but we use our cost model rather than executing the programs. So our cost model is going to predict the execution time. So let's see what's the effect of using our cost model. As you see in many applications, the whole optimization technique, our optimization technique using beam search plus cost model is able to match the ideal case. In some of them, it's a little bit slower. And in some of them, there is a quite significant difference, like in Jacobi 2D, for example. Sorry, in Jacobi 2D. And the reason for this drop is that Jacobi 2D has some patterns in the code that we don't have in our that we didn't have in our training data set. So the model was less accurate in the case of Jacobi 2D. Now, in the next experiment, we used the cost model to predict the speedups, but we changed beam search with Monte Carlo tree search. And Monte Carlo tree search has the advantage of being more stochastic, so it randomly tries things. And because of that, in the case of Jacobi 2D, this helped because the model started to randomly explore certain paths that it wouldn't explore if it just would have relied on the cost model. And in the last experiment, this one shows the advantage of using stochastic method like MCTS to explore the search space. And then in the last experiment, we compared to state-of-the-art compiler, which is the Halide compiler. This is a compiler that's being used now in production by many companies at Google, at Facebook, at Adobe. It has an auto-scheduler, so it's kind of state-of-the-art industrial scheduler. And as you see, our work is showing speedups higher than the Halide compiler. So for example, if you see here, we are about maybe we have speed up of 5, whereas Halide only has speed up of 1.5. Now, let me add this one more slide. Now you might say, which one is better? Is using MCTS plus the model better than using beam search plus the model? Sorry. And to answer this question, let's look at the following table. So the following table compares the three options that we have, basically beam search plus execution, which is the perfect. We use it as the reference, with beam search plus the model or MCTS plus the model. And it compares these 3 options based on based on the search acceleration, how fast is the search, and then also on the performance degradation in terms of the final result. if you look at beam search plus the model, it's about 100 times faster than beam search plus execution. Simply because when we use the model is faster than running the model is faster than executing the code. So that's why we are doing all of this work in the first place. So it is quite fast, but in terms of performance degradation, it's about 15%. So we lose 15% of performance in the final result, but we are 100 times faster in terms of optimizing code. If we use MCTS, we are about 10 times slower than using beam search, but the degradation, we improve the degradation in performance by 5%. So now we are just 10%. We have only 10% average degradation to the ideal kind of optimization. And now you have kind of trade-off between having slower execute code optimization module that would give you better performance compared to fast one that would give you a little bit less performance. So that's all for the presentation. I presented this deep learning model for automatic code optimization that achieves an accuracy of 16%. It's based on hierarchical tree LSTM and very simple basic features extracted from the code. And it was implemented on the Tiramisu compiler. You can find the Tiramisu compiler on this website, tiramisu-compiler.org. The compiler itself is open source. The model itself is open source. And then you can also find a link to this paper on that website. And if you are interested in reading more about this work, just please send me an email. I will be happy to send you the paper. So that's all from my side. And if you have any questions, please feel free to ask your questions.
Thank you very much, Riyadh. Merci beaucoup pour cette excellente présentation. Donc, on commence par le débat. Des questions? Y a-t-il des questions? Vous pouvez lever la main ou...
Donc, en gros, cette technique est actuellement, l'équipe de MathWorks est actuellement en train d'implémenter cette technique dans le compilateur de MATLAB. Donc, bientôt, il y aura une version de MATLAB qui utilise exactement ce travail-là. Et des techniques similaires sont en train d'être implémentées dans les compilateurs de TensorFlow XLA, dans le compilateur de PyTorch. Donc c'est un travail qui est actuellement en train d'être fait par plein d'industriels autour du monde.
Riyadh, il y a une question sur les messages. Il y a une question de mademoiselle Nousseiba Missaï. Je ne sais pas si tu arrives à...
Which step during this DNN processing we check that speeding up doesn't falsify the result of code? Yes, that's a very good question. Parce que j'ai cette slide, elle avait j'ai enlevé pas mal de slides. Mais en gros, le problème de optimization selection, on peut le décomposer en deux sous-problèmes. Le problème de space exploration, en gros, explorer l'espace de recherche, et le problème d'évaluer les candidats dans cet espace de recherche. Et la partie de candidate evaluation, on peut encore la décomposer en deux sous-problèmes. Le premier, c'est le cost estimation, c'est estimer le speed-up. Et le deuxième, c'est correctness check, voir si cette liste d'optimisation garde la correctness du code, assure que le code reste correct. Et pour le faire, donc pour la partie space exploration, on utilise des techniques classiques. Et pour la partie correctness check, on utilise ce qu'on appelle l'analyse de dépendance polyédrique. C'est une analyse qui a été développée dans les années 90 et qui nous permet de s'assurer que une liste d'optimisation peut être appliquée sur le code sans problème, sans falsifier les résultats.
Il y a une autre question, monsieur Khamouj Sharafdin. Tfaddal.
Je parle, monsieur. Tout d'abord, je remercie monsieur Baghdadi pour cette présentation. Vous m'entendez?
Oui, oui.
Oui, oui.
Je remercie monsieur Baghdadi pour la présentation. Merci à vous monsieur Kermid, aussi pour l'organisation de ce webinaire. En fait, j'ai deux questions. La première, par exemple, dans l'exemple cité pour l'opération Reduce Spam XYZ. Point de vue mémoire. Donc, on va revenir, c'est-à-dire on va consommer le même espace mémoire parce que en décomposant l'opération par la suite, en décomposant l'opération, donc on va utiliser le même espace mémoire.
Le but principal, c'est d'utiliser les registres au lieu d'utiliser la mémoire globale. Donc ça, c'est le but. Le but ici, ce n'est pas de réduire l'espace mémoire, mais effectivement, si on applique cette optimisation aussi, on réduit l'espace mémoire utilisé. Parce que ici, d'abord, quand on multiplie Y avec Z, on stocke le résultat dans T1. T1, c'est un grand vecteur. Ensuite, on utilise T1 et on stocke le résultat dans T2. Ensuite, on stocke notre résultat dans T3. Alors qu'ici, on fait toutes les opérations sur les registres et on stocke le résultat final sur T1. Donc, ça réduit l'utilisation de la mémoire. Mais surtout, ce qui nous intéresse, c'est que ça réduit les accès à la mémoire.
D'accord, monsieur. Merci, monsieur, pour la réponse. Ma deuxième question, monsieur Baghdadi, vous ne trouvez pas que pour un développeur, l'utilisation des bonnes pratiques de codage, par exemple l'utilisation des threads pour le parallélisme des opérations ou bien dans les boucles, est plus efficace car ici, c'est vrai, on gagne du temps d'exécution, mais en contrepartie, on va perdre de temps pour l'apprentissage ou bien pour mettre en place c'est-à-dire des fonctionnalités ou bien de prédire quelques opérations. Donc, on va perdre de temps pour l'apprentissage. En plus, peut-être la qualité, on perd aussi la qualité de la solution finale.
Oui, oui. Oui, je suis d'accord, mais le but, ce n'est pas de demander aux utilisateurs d'utiliser Tiramisu directement. Le but, c'est d'intégrer Tiramisu dans des compilateurs et des frameworks qui existent. Donc, l'utilisateur final va utiliser PyTorch ou TensorFlow, et automatiquement à l'intérieur, dans PyTorch ou bien dans TensorFlow, toutes ces optimisations vont être faites. Tiramisu en lui-même, c'est un compilateur de recherche, donc le but, c'est de développer des idées et ensuite les prendre aux équipes qui travaillent sur TensorFlow et PyTorch. Et actuellement, ces équipes-là sont en train d'implémenter ces techniques. Donc, sont en train d'implémenter ces techniques d'optimisation automatique dans PyTorch et TensorFlow. Le deuxième problème, oui, il y aura ce gap, cette différence entre un code optimisé manuellement et un code optimisé à la main. Toujours, l'optimisation manuelle sera peut-être 5%, 10%, 20% mieux. Mais le but ici, c'est de permettre aux utilisateurs qui ne sont pas des experts de bénéficier de ces optimisations. Et s'il y a quelqu'un qui veut vraiment pousser les performances, il peut faire les optimisations à la main. Et faire ces optimisations à la main, c'est nettement plus complexe que juste utiliser des threads pour la parallélisation. Donc, c'est vraiment très, très complexe. Rien que pour optimiser la multiplication de matrices, il vous faut peut-être 6 mois de travail et beaucoup, beaucoup, beaucoup d'expérience.
D'accord.
D'autres questions? Donc, si vous permettez, j'ai une question, Riyad.
Oui.
Bon, à vrai dire, ça fait plus de 5 ans que je travaille avec les collègues, avec mon équipe, sur le deep learning. notamment sur les CNN tridimensionnels, les DNN, etc., pour un domaine d'application bien précis. Il s'agit de la segmentation et l'extraction des tumeurs cérébrales avec ses différentes composantes en IRM, hein, en imagerie par résonance magnétique. Et actuellement, je travaille sur la détection des lésions pulmonaires dues à la COVID-19 à partir des TDM, des scanners rayons X, des images à rayons X. On est souvent confronté au même problème depuis des années, hein. D'un côté, on cherche d'avoir une segmentation précise, donc il s'agit d'exactitude, et d'un autre côté, c'est le problème des ressources mémoire. Quand on travaille en 3D, cela nécessite vraiment des ressources mémoire très importantes pour pouvoir aboutir à des résultats. Donc c'est un trade-off, donc c'est un compromis entre l'exactitude de la prédiction et d'un autre côté la rapidité de traitement, de training surtout, l'apprentissage. Donc, on a utilisé le cluster Ibn Badis des siristes, d'accord. Et par la suite, on s'est orienté vers le collab de Google. Mais récemment, c'est restreint. Ils ont encore restreint les ressources mémoire. Donc, qu'est-ce qu'on fait pour aboutir? On essaie de trouver un compromis. Donc, le problème, c'est qu'on diminue le nombre de couches. Donc, on diminue la profondeur au détriment de l'exactitude. Et pour fixer justement les paramètres, donc il s'agit d'un problème d'optimisation. Je me demande, voilà, et jette l'idée, est-ce que, donc vous avez dit que le Tiramisu, il va être intégré dans TensorFlow et PyTorch,
Oui, oui.
dans les librairies. Est-ce qu'actuellement, ils sont intégrés on peut les trouver sur Colab? Pas encore, c'est en cours?
Non, pas encore. Justement, c'est un travail qu'on est en train de faire. Donc, il y a une version très, très préliminaire qui intègre Tiramisu dans PyTorch, mais elle n'est pas, je ne pense pas qu'elle est prête pour être utilisée en production. Par contre, je sais, parce que j'ai mes collègues qui travaillent chez Facebook sur PyTorch et sur TensorFlow chez Google, je sais que d'ici bientôt, quand je dis bientôt 1 an, 2 ans, il y aura des versions disponibles en open source qui optimisent automatiquement. Il y a aussi un autre compilateur qui s'appelle TVM. Donc
TVM, oui.
C'est un compilateur similaire à Tiramisu et qui fait ces optimisations automatiquement. TVM, ils ont créé une startup autour de cette idée. La startup a eu plus de 150 millions de dollars de financement. Et c'est exactement ce travail-là. Mais eux, ils ont vraiment poussé les choses parce que c'est une entreprise. Donc, ils ont un travail en production.
C'est TVM. TVM.
Il y a aussi j'ai oublié comment ça s'appelle. Je pense c'est un truc de Microsoft. Il y a le terme, I think, Zero Memory ou un truc comme ça. C'est un module dans PyTorch qui optimise l'utilisation de la mémoire.
C'est payant ou c'est gratuit?
Non, c'est gratuit. Tout est gratuit.
Très bien, tant mieux. On a ce qui est gratuit parce que parce que vraiment, c'est ça le problème, en fin de compte. Les modèles qu'on conçoit, on ne sait pas, c'est-à-dire, quelles sont les limites.
Oui.
Parce qu'on essaie de diminuer. Des fois, où nous l'image, on fait des cropping, on fait de drop-out, les couches, afin d'accélérer le traitement, mais au détriment de l'exactitude. Donc, on essaie de jongler.
Surtout en 3D. Surtout en 3D.
Oui, en 3D. Oui. Non, pas seulement, Riyadh. Il y a un autre problème, parce que l'IRM, par exemple, ce qui est tumeur cérébrale, on travaille sur des images multimodales. Pas une seule IRM pour un seul cas clinique. Il y aura 4, vous imaginez un petit peu, 4 volumes en parallèle, en plus de ground truth, en plus de l'apprentissage, en plus de la vérité de terrain, pour que le modèle puisse apprendre. Donc, on a mourir des zones d'intérêt au détriment de l'exact. On n'a pas le choix de toute façon. Hein. si on avait une machine très rapide au sein du laboratoire, peut-être ça peut nous débloquer la situation, même à casser, ça reste insuffisant. Voilà. Merci pour la réponse. D'autres questions? Il y a une question sur les messages. يخلف على الدين. Je sais pas, Riyad,
Oui, oui. Pouvez-vous nous donner une idée, si possible, comment les frameworks utilisent le Tiramisu compilateur pour l'optimisation? Oui, donc en gros, l'idée c'est en tant qu'utilisateur, vous allez utiliser PyTorch, on va dire PyTorch. Donc vous utilisez PyTorch pour décrire votre modèle. Et ensuite, PyTorch en lui-même, quand vous lancez l'exécution de votre modèle, PyTorch va appeler Tiramisu, qui va prendre, actuellement c'est ce qui se fait, qui va prendre les opérateurs. Il va d'abord créer un graphe de computation. Ça, c'est PyTorch qui le fait. Il crée un graphe comme ça. Ensuite, il va appeler Tiramisu. Tiramisu va parcourir ce graphe. Et il va faire des décisions de est-ce qu'on fait la fusion, on ne fait pas, etc. Et ensuite, pour chaque opérateur, supposons qu'il décide de faire cette fusion, de faire comme ça, pour chaque opérateur, il génère un code Tiramisu équivalent, il l'optimise automatiquement, il remplace juste cet opérateur. Parce qu'en gros, dans PyTorch, quand vous appelez un opérateur, en fait, vous êtes en train d'appeler, de faire un appel à une bibliothèque qui implémente, par exemple, Y fois Z. Donc, nous, ce qu'on fait, c'est que Tiramisu va générer un code à cet opérateur, il va faire l'optimisation automatique, et il va remplacer cet appel, cette partie-là, par le code généré par Tiramisu. Et donc, le tout sera fait de façon transparente à l'utilisateur.
D'autres questions?